Hello everyone, this is lecture 18 of Advanced Drilling Engineering, PTRE 451545. Today we'll proceed with module 3. I haven't uploaded homework 4 yet because last night I was busy with the presentation on the I got home around 10 and then I had to work on the presentation for the outreach that our SPE chapter is doing. That's why there is no students in the class, I guess, today. But they are going to be doing an outreach activity today and tomorrow. They are going to do 2 days, 5 sessions every day in a local high school or middle school in East Grand Forks. And they are going to talk about petroleum engineering, the Society of Petroleum Engineers, and they are going to do 2 hands-on activities. One of them is core sampling. Basically, they are going to make a cake, multiple layers, etc., etc., and they are going to try to take a cylindrical sample which shows all the layers using a straw. That's for the younger students. And the older students are gonna do like a small fracturing gelatin block, a gelatin block. So they had to stay here. Yesterday they were at the lab preparing like something like 17 gelatin blocks, which wasn't an easy process. And also they are gonna make a presentation, etc., etc. So I was busy with this stuff last night, and I wasn't able to finish the homework, and I don't want to give upload a homework that is not reviewed well, because you saw what happened in the previous homework. And the reason was for the whole confusion in the previous homework is that when I was making a solution to the homework, I make the wrong plot initially, and then I fixed it, but I didn't delete the bad, how do you say, the wrong plot. And 3 years later, when I was seeing it again, or 2 years later, because the first time I gave that homework was 2023. Now, 2 years later, I forgot about that, and hence there was the whole confusion. But for this one, also homework 4 is easy. Homework 4 is supposed to be easy. And then we have a homework 5, which is longer. It's going to be the hardest homework for this class. And then project part A and project part B, and we are done with the semester. The exams have been graded, but the results are not on Blackboard yet. Kalu showed me the results, and I reviewed all the exams. 77 is the average, which is good. The highest grade was 100. The lowest grade was 28. Average 77. Nice, good performance. What I was going to say about the exams, they should be in soon. You know, Kalu is very busy with this event today and tomorrow. The TA, so yeah, give him a little bit of time just to put the grades on Blackboard. I have seen the grades, and I have seen the exams actually. One thing I want to specify is that we didn't take grade off, points off, but weight on the bit decreases when you get a kick. Okay, yes, it's an independent parameter. You apply it. But if you keep it constant as it is, if you have it on auto, when you are drilling and you get a kick is pushing the drill string up, okay? So the reading that you have of the weight on the bit decreases, it goes down. Some people didn't put it in the exam, and I was gonna make the TA take 1 point off, and then I realized that it's only gonna help people. It's not gonna help anybody. If I take a point off for that, I just want you to know, because if you go for once you are finished with this class, you are supposed to be ready to go and take the well-controlled class, the first well-controlled level. You should be able to clear it real easily. But those, it's not seminars, those like industry courses are very, very tough, okay? They are trying to intimidate you intentionally. They are trying to make you work under pressure. So it's not gonna be an easy 3 days if you go and take these courses. So, and these are fundamental stuff, key indicators. I want you to know them very well, okay? It's like, it's a must. So I want you to be very, very comfortable with this. Like, you know, ROP goes up, WOB goes down. Mat out is bigger than mat in. I get a pit gain. What else? Yeah, this kind of. Then I start seeing oil cut or gas cut in the mat. These are stuff that really you're on the lookout for when you are drilling for a kick, you know, very, very important. I get cuttings that get bigger and bigger. All this stuff. So I want you to be very, very familiar with those, even though we didn't take a point off. I mean, okay, in the exam, I don't care, but if you go for a well-controlled class, well-controlled fundamentals class, they are gonna be expecting you to know that, and they're gonna teach it to you very fast. So I want you to know them from the class, you know, very well. So anyway, good job in the exam. I will proceed with, let's proceed with module 3. And last time we talked about the leak of testing. We saw 3 ways we can do leak of testing. And I know some of the slides need fixing, and I will do that too. Need to do that. We talked about Hubbard and Willis method, Matthews and Kelly. Etons, we talk about Eton has the Poisson's ratio varying. Never ever give a Poisson's ratio bigger than 0.5, okay? Something is wrong if you read a Poisson's ratio bigger than 0.5. I was at the American Rock Mechanics Symposium last year, and there was a student who put Poisson's ratio 0.73 on his poster, okay? I confronted the student, and he's like, oh yeah, I put it in I went to the lab, I put it in a machine, it gave me 0.7, and I put it on the plot, okay? This is bad. This is not how you do science, okay? If the machine gave you 0.7, there is a reason why it gave you 0.7. It doesn't mean that it's the Poisson's ratio 0.7. It was reading 0.7. An apparent value of the Poisson's ratio was 0.7, maybe because of something related to the material. The way the material was behaving, it made the machine think that it's 0.7, okay? Multiple layers, one pushing each other. It was a synthetic sample, something like that. But it doesn't mean that the material had a Poisson's ratio of 0.7, okay? It's bad. And this is, other people are seeing it and they think that this student doesn't know anything. And then they say, oh, which school does he come from, okay? So this is stuff that you guys need to be very careful about. And I know there are some advisors that they are not really on top of managing their students, but please be careful with this stuff. If you are in the lab and your job as a researcher is not to test something and whatever you read, you put on a paper and you publish, and then you tell your friends to cite you. And then you say, oh, I have a lot of citations. And then you go and get a job and that employer thinks you're amazing, and then it's gonna be a nasty fall to reality. Please be very careful. But yeah, don't expect a Poisson ratio bigger than 0.5, obviously. And for rocks, don't expect to see something less than 0.1, 0.15, something like that. Okay, now the people doing gelatin experiments like Kalu, that's as close to 0.5 as you can get. Okay, we assume in his work that we are really dealing with something like 0.5, 0.45, 0.47, and that's as close as you can get. In rocks, I wouldn't expect you to go over 0.4. For cement, and that would be a very big exception. For cement, is 0.33, 0.33, 32, and that's pretty high. That's pretty high. That's a very, very well blended cement. Okay, rocks are it's gonna be lower. 0.15, 0.25, 0.27, 28, 3. That's what you expect to see in the rock. Anyway, so we saw all the methods except one, which we're gonna see today. The Christmas method, 1973, which again now has a new term called F. Is F times SV minus FPP divided by TVD plus FPP divided by TVD. Okay? Now, what is this F? It's the stress ratio calculated using fracture data from nearby wells. It's basically including all this stuff, ni divided by 1 minus ni, and the constant that you are missing from the other fraction. They are grouped together into a new term called F. Okay, it's basically a modification of Eaton's method and is designed to predict fracture gradient in offshore fields. Okay, remember Eaton's correlation was derived using data from the Gulf. What is now Gulf of America back then was Gulf of Mexico. So it's very good for this kind of numbers. And this Christmas method is an adaptation of Eaton's method, okay? And it's an empiricism, basically. Well, it's a physics-based empiricism, okay? You have some physics-based inputs like SV, FPP, TVD, but you also have the data-driven factor F, okay, stress ratio, which is to a large extent data-driven, in all honesty. So, and also notice that these equations, they are really from the 60s and 70s and 50s, back before people had computers well into their workload. People were working with slide rules and they were working with slide rules and tables. So really using those equations was taking a big part of their shift. Nowadays, all you need to do is take your calculator, bing, 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 and you give me a number, okay? So you can use all these equations, find a bunch of numbers, give me a range if you wanted to. Or use some more data-driven approach. It's just, you know, it was, how do you say it? These equations are supposed to give you a ballpark, okay? And then you apply a safety factor, and you are basically never going near this number, you know, because if you exceed the fracture gradient when you are drilling, you have a problem. Anyway, also undergrads are gonna take geomechanics next fall semester, and you are gonna see that these fracture pressures they are not just one number. It's like you can have different types of pressure of fractures. everyone has a different fracture, every type has a different fracture pressure or fracture gradient value associated with it. And the one that is most likely to happen, or the one that you need to be aware of, is the smallest one. Okay, and that has to do with the stress field in the near wellbore. We said at the beginning of this module that the stresses are given by Andersonian simplification, which basically said that, okay, let's assume that you have three stresses that are mutually orthogonal in the Earth subsurface. The vertical, we're going to call it SV, and the horizontal, we're going to call it SH max and SH mean. This is a simplification. Real life is much more complex. But Anderson said that for the depth that we are interested, if we make this a simplification, we are good enough. Okay? Now, when you drill a wellbore, which is what you learn about in this class, you are removing a rock, right? You are removing volumes of rock. And you are replacing that with fluid. Okay, this disturbs the stress field around it. So if you go near that wellbore, the stress that you see is no longer as VSH max SH mean. It's a different kind of stress state, which is related to SVSH max and SH mean, but also related to the pressure inside the wellbore. What we call the wellbore pressure, okay? Similar to, which is basically the weight of the mat that you are learning in this class. So because of the shape of the wellbore is cylindrical, it's not a good idea to use Cartesian system in the near wellbore, region. Instead, we are using what we call cylindrical polar coordinates. And I have a typo here that I should have fixed. R, theta, and Z should be at instead of X, Y, and Z. And then you need to have X, Y, and Z instead of R, theta, and Z. I will fix that. So this needs to be replacing this. And vice versa, I guess. I will fix that. Sorry about that. I made the same. I fixed that in the other class notes, but not on this class notes, which was stupid. But anyway, we have a new set of stresses that I don't want you to know crazy a lot about, but you know, if you are near the wellbore, you have a different kind of stresses, a different set of stresses, and those are not in Cartesian coordinates, they are in cylindrical coordinates. I want you to know their directions because it's going to become very important later on in other classes. So it's good if you understand them from now. So let's just say I want the stress state in this place here. I'm fairly close to the wellbore. Okay, I draw a radius from the wellbore to this point, and I extend it with a green arrow. We call that sigma RR, or the radial stress. Okay, then I go orthogonal to that with a red arrow, and I call that sigma theta theta. This is the tangential, also known as hoop or circumferential stress. Okay, that's perpendicular to the radial stress. And the radial stress is as if you are extending the radius from the center of the web. Then up and down along the wellbore length, I use a red dot to indicate something that goes into the plane of the screen. That would be the axial stress sigma ZZ, blue axial stress. And then with the pink, I will use some different kind of arrows. This will be sigma R theta, the shear stress, okay? Radial, tangential, and axial stresses are normal, okay? It's a different kind of stress. It's a normal kind of stress. what you learn in solid mechanics is normal stress. And the sigma r theta is the shear stress. Okay, it's not normal, it's shear. Okay, let's try to go in the wellbore radius on the wellbore walls. Okay, I want to write this. I want the stress at this point here. Okay, so I draw a radius to that point. I extend it with a green arrow, and I call that sigma RR, the radial stress. The arrow, whether it's here or here, I wouldn't worry that much about it now. Here means compressive, okay? Here means tensile. I'm drawing it tensile so it looks better on paper. It looks clearer, but it doesn't mean that it's tensile. Or it could be compressive. This would be the tangential stress, sigma theta theta, and then I will use a dot or a cross for an arrow basically going into the screen of the rock. What I was gonna say? Oh yeah, that is basically a stress into the screen. Like imagine if the wellbore is like this, the stress is like this or like this. Okay, it would be a cross if it's going down. It would be a dot if it's coming up, but you don't care about the direction of the stresses now. Sigma ZZ. Okay. Now you are going to ask me what about the shear stress, and I will tell you something that I want you to keep like how do you say, take it for granted, and I will explain it. It will become clearer later on in other classes. Like I will say that on the wellbore walls, shear stresses go to 0. Okay, and I will prove that to you mathematically next class. But take it for granted for now, okay? I'm saying it as a how do you say, like I want you to take it as a given, okay? Take it as a knowledge, and then I will prove it to you later on, because I don't want to show you the equations for those stresses right now. I will get you confused because we are going to go through them in more detail in other classes. Right now, I want you to know the directions of the stresses and the names of the stresses, so you are familiar with it. The directions I mean not the arrows, where they are pointing, like the configuration of the stresses and their names, of course. I want you to know far from the wellbore, I have SB, SH max, and SH mean. Near the wellbore, I have radial, tangential, axial, and shear. And on the wellbore, the shear goes to 0. That's all I want you to know for now. We're going to see equations for those stresses later on. Okay, now the equations for those stresses, well, we're not going to see them, but we are going to talk about a little bit of a history, because the equations for those stresses are extremely, extremely important. extremely important, especially for us drilling people. We care about what is the fracture pressure on the wellbore radius, right? So we need to know the stress state on the wellbore radius. It's also important for completions people. They want to initiate fractures on the wellbore radius, hydraulic fractures, right? These fractures, they are going to start from the wellbore radius. Just like when you are drilling, you don't want to start fractures, what we call underground blowout. This is a fracture from the wellbore radius. So I care very much about the stress state on the wellbore radius. And this has been a mathematical problem for years and years ago. Okay, Lamé and Clapeyron in 1831, they were working for stresses. They wanted to see how much you can load a cannon before it explodes. Okay, they were French people. It was, I guess, war times in France. And they were asking, hey, how much can we load the cannon before it explodes? To do that, to know that, you need to know the stresses in the walls of the cannon. And they derived some very nice set of equations called, ironically, it was called the Lamé equations. They dropped Clapeyron's name from it, I guess. I don't know why. But what is known as the Lamé equations today, this is what Lamé and Clapeyron derived in 1831. Clapeyron, you come across him in thermodynamics when you do about the Clausius-Clapeyron equation. What's the name of that equation? It's an equation of the, I forgot the name of the vapor pressure variation with temperature, something like that. I don't remember from thermodynamics. But there is the very famous equation, Clausius-Clapeyron. And obviously, Lamé, you are going to see again in geomechanics. Lamé is one of the names on Eiffel Tower. They have names of famous French people, and Lamé's name is on it, okay? Just like Poisson is on it. And another one that starts with C, Cauchy is on it. Cauchy is at the end, at one of the edges. There is more people on it as well. I don't remember. But those famous French people who worked on Lagrange, and Lagrange wasn't really French, he was Italian, and then moved to France. A lot of people they have their names on the Eiffel Tower. Then it was Kirsch, who was a German professor in 1898. By the way, let me make a parenthesis. You saw those Lamé equations. If you go to your book and you read about the stresses inside the casing last year, when we did about casing stability, and we did about the von Mises ellipse, the stresses that you are using was the Lamé equation, the Lamé equations. I didn't go in deep enough because there is a little bit of a confusion. That part of the book was written by people with mechanical background, and they are using tension as positive and compression as negative. This is what you guys do in statics and solids classes. You use tension as positive, compression as negative. In geomechanics and in the petroleum engineering world in general, we do the opposite. Because we have a lot of compressive stresses compared to tension, we try to use compression as positive and tension as negative. And I intentionally didn't get too much into this kind of stresses because it will have been very confusing. I know some of you have not taken, are taking studies at the same time. Some of them did not take solids, and I didn't want to get into it in that much detail last year. And I don't know, I probably need to include that section in a class that comes later. But back in my day in Texas, we had to pass solids before we take drilling. So it was a little bit easier for our teachers at the time to get into this stuff during the drilling class, but we only had one drilling class. And it had a lab, and it was a nice class actually. Anyway, so we have Lamé equations, which is after Lamé and Clapeyron. Then many years later, 67 years later, if my math is correct, Kirsch, who was a German professor, a German engineering professor, he was a theorist. He was something like an applied math, mechanical engineering professor kind of guy. He took these equations and came up with a hypothetical conceptual problem, which is basically, let me use a different color. I have a plate. The plate has a hole in it. The hole is pressurized. It has tensile stress applied on its walls, pointing outwards. And the entire plate is loaded with a confining stress, okay? Sigma 1, sigma 1. And I guess it's the same sigma 1 and then on the side, okay? Then somebody came by, I don't know who. And by the way, this pressure inside, let's call it P, okay? It was a hypothetical problem. It didn't have an application, real life application, okay? Remember, Lamé was a canon guy, mathematics guy, Clapeyron the same. Kirsch was an engineering professor. None of them was geologists or petroleum engineer yet. It wasn't applied to the earth yet, this mathematical problem. Okay, somebody came by who I don't know, and I tried to find out, I don't know who took Kirsch equations and made one of the stress stronger than the other. So we have a sigma 1, and then you have sigma 2. So he changed the equation to a bi-stress loading or biaxial stress loading, something by whatever loading. So he changed that. I don't know who that was. And my advanced drilling professor also used to say he didn't know who that was, who did that. But that happened after Kirsch. And then there was another guy called Inglis in 1913. He made this ellipse. He made the hole, instead of fully circular, an elliptical one. Okay, I don't know if it was before or after the biaxial loading, but what Inglis did was, I think, for a single loading, not biaxial loading. Anyway, so a lot of things happened, and in 1957, we have Hubbard and Willis, who took this model and they said, why don't we call P wellbore pressure? And then we call sigma 1 and sigma 2 SH max, SH mean. And basically, this problem is applied to oil wells. And it's like excellent, 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 excellent. Hubbard and Willis, they were geologists for shale. Hubbard was a very smart guy. He got his PhD later in life. I think he was like my age. He was like 34, 35 when he got his PhD from University of Chicago. And he was from San Saba, which if it's the same San Saba, I think it is. I did stop by one time outside Austin. I was driving towards the oil fields, and I stopped at the Dairy Queen and at a Dairy Queen, and I asked the lady, "What place? What town am I in?" And she said, she told me San Saba. It's like outside in the outskirts of Austin, I guess. I think it was my last time I was heading to the oil field. Must have been December 2021, mid-December, somewhere there. If I remember well. And anyway, he was a very, very smart geologist working for Shell. And it was back in the day when people were divided into horizontals and verticals. Some people were saying all our fractures, all the fractures are from a well is vertical, all of the fractures are horizontal. And Hubbard and Willis came by and said, no, some fractures are horizontal, some fractures are vertical, and it depends on the stresses where these fractures start. The stress field where these fractures start. And he did a simple experiment in gelatin. He was the first one to use gelatin to imitate the rock, just like the students are going to do today in the outreach. He used a gelatin solution, injected fracture with cement, and the cement set, and the fracture, then he removed the gelatin, and he showed the fracture. He did two different configurations and made he showed vertical fracture and horizontal fracture. Well, it was a vertical well, so vertical fracture is what we call longitudinal these days, and then horizontal fracture is what we call transverse. And this is the best paper in SPE's 1 Petro. Okay, you should go and read it, download it. It's called Mechanics of Hydraulic Fracturing, 1957. It's probably the best paper in 1 Petro. And he was a very, very well-mannered, very, very flamboyant guy. You can read the discussion on the paper. Some people had their complaints about the paper, as you can tell. And then he responded to those discussions in a very, very eloquent manner. He was a very, very flamboyant character, from my understanding, Hubbard. Of course, he's famous for something that he did the year before, which was the Hubbard's peak oil theory, which was a very, very questionable sort of, it was good for the short term, but it got heavily debunked later on. Like it was a time-dependent concept, I guess. I think it was a symposium for a celebration for 100 years from Darcy's equation, where he presented the Hubbard's peak oil theory. You understand that it was like he predicted a peak in the oil production, and he got it within, in the global oil production, he got it within 1 year. I think he predicted it from 1970, and it came in 1971 or he predicted it from 1971 and it came in 1970, something like that. He missed it only by a year, but you understand that now we are millions of barrels a day above that projected peak oil. But his real work came, his best paper is this one, Mechanics of Hydraulic Fracturing. And it was very well written. The last paper I wrote, when I was a postdoc in Colorado School of Mines, I was not in oil and gas. I was in civil engineering, and I was investigating stability of tunnel intersections, and I used that paper as a template in a sense in terms of structure and I guess stylistically speaking, because it was very, very good paper. I suggest you go and download it and read it from Juan Pedro. And you can see pictures of his experiments. He did the experiments and he showed them, he proved to them that yes, it can be longitudinal, it can be horizontal fracture, it can be vertical fracture. It all depends on the stresses on the stress field, or where the fractures start, basically. And then we have another set of geomechanics people, Himson and Fairhurst, who were in University of Minnesota, and they modified the Kirsch equations. By the way, what did Kirsch add to the equations? He added the pore pressure, okay? He added FPP, what he calls P sub P, PP. In geomechanics, we call it capital P, sorry, P and subscript P, pore pressure. In drilling, I guess we call it FPP. It's the same thing. So this is what Haber and Willis added. And Haber died in '89, I think. I read his obituary. He went to a club, a bar or something at night. And the next day he didn't wake up. I guess it was a good night out. But yeah, he was in his 80s when he died. He died at 89, yeah, a few months before I was born. Marion King Haber, whatever his name was. He also did a lot of work like tilt meter. He invented something with a tilt meter, and it was like completely randomly. They were having a field trip with some geologists, and they were drinking beer, and the beer can was moving a certain way, and they understood that it has to do with the curvature of the surface of the earth based on fractures underneath the earth, underneath the surface, and from that they came up with some other concepts. But yeah, he was a very, very smart guy. Anyway, and then we moved to Himson and Fairhurst. Himson is Bezalel Himson, who's actually a member of ARMA. I don't know if he's still alive. I think I saw him in the ARMA Symposium of 2019, that was in New York. But he was the student of Fairhurst. I want to say it's Charles Fairhurst. They were a professor and student pair in University of Minnesota. Now you will know that University of Minnesota has a very famous rock mechanics group. Okay, and out of that rock mechanics group, Itasca came. Itasca Consulting Group. They sell software, rock mechanics software that is used by civil engineers, petroleum engineers, chemical engineers, hydrologists, geoscientists, etc., etc. A very famous software that they use is Flag 3D. Fast Lagrangian analysis of continua. It's basically a geomechanics simulator. They were, I mean, I guess that was the beginning of that very famous rock mechanics group in University of Minnesota. not very far from here, like 6 hours. And what they added to Haber's equations was they added poroelasticity, which is something, it's a mathematical complexity due to changes in the size of the pores with changes in pressure inside them. So you know that the rocks have pores, and the pores are filled with fluid, and this fluid is under pressure. Okay, this is what Hubbard and Willis accounted in the equations. They incorporated that pore pressure. Now, if you change the pressure inside those pores will change, and this is called poroelasticity. Okay, it's mathematically very complex. There's people who do their PhDs and spend their careers investigating poroelasticity. It's a very complicated thing. At classroom level, we restrict ourselves to a very simple form of poroelasticity, what we call colloquially linear poroelasticity. Some people say this is not even poroelasticity. Okay, the thing is that poroelasticity is like a dynamic aspect, which means related with time. Most of the equations we have seen in the class are static. Okay, linear poroelasticity is a pseudo-dynamic sort of concept, fake dynamic, not a real dynamic concept, but it's simple. It's simple enough to be able to derive some fairly easy to use equations, etc., etc. So Higginson and Fairhurst and Hubbard and Willis is as deep as we will ever go to in classroom level, mostly Hubbard and Willis, to be honest with you. Okay. But now we are really interested in drilling, not in completions. Because hydraulic fracturing, we are going to see this stuff in other classes as well. What about drilling? Okay, I'm actually drilling a rock. I'm removing rock volume. I'm replacing it with fluid. And we talk about the mud window, etc., etc. In real life, okay, my mud weight is never perfect. Okay, it goes a little bit to the left, a little bit to the right. I get instabilities, okay? I get instabilities, but I don't necessarily get kick or low circulation yet. I have like imperfections in the way I'm drilling a hole. Sometimes my mud weight is a little bit too high. Sometimes my mud weight is a little bit too low. It changes, it alternates, okay? This is manifested on the borehole walls as washouts if my mud weight drops low, or drilling induced tensile fractures if the mud weight is a little bit too high. Also, when I see the borehole, it's going to be a little bit of an oval shape. The small sides of the oval shape, the long against radius direction, which is this, because if it's looking like this, I'm looking at here. This is too oval. Here, this is basically washouts or breakouts or borehole breakouts or wellbore washouts, whatever you want to call it. This is called wellbore washout. This is the washout. This is when the pressure inside the wellbore pressure is smaller than what needs to be. Okay, it's just before a kick is about to happen. Okay, you get a washout. If you keep doing it, you will get a kick. Okay, if you keep becoming more and more extreme, you get a kick. Across to it, sorry, it doesn't let me draw below the, but this stuff here and this stuff here is something that we call drilling induced tensile fractures. Okay, that's when your wellbore pressure is too high. You create a fracture that opens like this. This fracture is essentially speaking a hydraulic fracture, or geologically speaking, an artificial dike with an eye, which is basically the same thing as a magmatic intrusion. It's a tensile fracture, okay? Whereas borehole breakouts, they are shear. This stuff here is shear. This is tensile. What they say here, induced fracture. Drilling induced tensile fracture, okay? And when I'm drilling, I can use a special kind of log called image logs, and I can see both of them actually. Okay, if it's a vertical well, SH min would be the direction of the breakouts or washouts, and SH max would be the direction of the drilling induced tensile fractures. And so on and so forth. Now, these are imperfections during the drilling process. You understand that. But they also have a very huge diagnostic power, because if you run an image log, you are gonna be able to trace those. And the more now when you see an image log, it looks a little bit confusing, maybe intimidating, but the more you train your eyes at looking at image logs, the easier it will be to identify borehole breakouts from the fuzzy black color, etc., to drilling induced tensile fractures from the narrow but very dark, very strong dark color compared to the breakouts for the drilling induced tensile fractures. Drilling induced tensile fractures is narrow and dark. Breakouts is fuzzy, dark, less dark, but still dark, and fuzzy, like more wider. So eventually there is geophysics who look at image logs every day. These people are the best one to ask them to show you an image log and discuss the difference between borehole breakout or wellbore breakout and drilling induced tensile fractures. Dark patches versus darker, I forgot the R here, narrower lines. Now, drilling induced tensile fractures, they have a distinct orientation with respect to the wellbore. Some of them are transverse. They cut the wellbore orthogonally. If it's a vertical wellbore, it would be like this, or longitudinal along the axis of the wellbore versus transverse. Okay, the directions are important. This orientation is very important. Okay, so this about the wellbore mechanics portion of the module. And we are going to move to the directional drilling portion, more applied portion. You are probably going to like it more, but this part that we did already, we are going to dive deeper next class in geomechanics, and then the class afterwards in completions or advanced stimulation techniques. Okay, I have a lot of messages, but everything is okay. Busy day today. Okay, any questions about what we covered already in module 3 in terms of wellbore mechanics before we get into directional drilling? Okay. I know some concepts are a little bit confusing for you guys because, especially if you're undergrad, you never dive, you did not dive deeper yet. But it's going to become clearer the next time you see them and the time you see them afterwards. It's you are not friends with those concepts. You are not quite friends yet. You will become friends with them. And once you become friends with them, you will be, it's going to look less intimidating. So yeah, don't be intimidated by this stuff. You get more chances later on. So directional and horizontal drilling, those are not the same thing, as you can understand. And the speaker last Friday actually explained the difference between the two. Directional drilling or extended reach drilling, which is an extreme form of directional drilling, is that I'm navigating towards a target far away from me, whereas horizontal drilling, I'm drilling vertically, and then I go horizontal inside that target, okay? Directional drilling is dividing the borehole along a planned course to a subsurface target whose location is a given lateral distance and direction from the vertical, enables reaching deep formation targets even at considerable horizontal distance from the surface rig. Is the old joke that they used to say since I was a freshman, that you can put a tractor tire at the 50-yard line in the football field, in the UND football field, and we can bring a rig here and start drilling from this building, and we can have the bit go through this tractor tire in the 50-yard line of the football field. That would be a nice activity. Imagine how many views will that get. But anyway, directional drilling technology is very, very state-of-the-art. Directional drilling technology is very, very high-tech. It's very similar to space navigation technology. In fact, the argument is that it's not just me making the argument, that it's actually better because in space, people see where they are heading, whereas we don't. It may be dark, but they see. For us, it's dark and we still don't see. What I was going to say. During the drilling process, on the basis of the information as and when it is relayed to the directional driller by a geologist called geosteerer, both the inclination and direction can be modified. And this is called geosteering, the real-time changes in the direction. So what happens is that the geosteerer gets information from the mud logger, the well site geologist, and tells the directional driller where they are and where they need to head. And the directional driller makes the mechanical changes on the direction of the hole as they go deeper and deeper, as they go, as they drill through or drill on, I guess. So, those are quite a bit of directional drillers are always the characters, like very weird people. Directional drillers. You know, every rig has a diva. Most of the time, that is a directional driller. I used to be on a rig in New Mexico. The directional driller was a real diva. I mean, he was really coming to our safety meetings wearing fluffy pink flip-flops. Every time off, he was going to Las Vegas. Anyway, they make a lot of money. And their cabins are very near the geosteering person. The geosteering person may not be in the well, in the rig, may be doing 4 rigs at the same time. Okay, so he may be in one of those 4 rigs, but he gets information by, I guess, the geologist who is on the rig, and then there is a big geologist in the office sometimes. And yeah, I mean, what does the directional driller control is basically something called the tool face angle. And this is what he manipulates. But the information he's getting from a directional survey is inclination angle, azimuth, and measure depth. Okay, he gets these 3: azimuth, inclination, and measure depth. And he wants to manipulate the tool face in order to, and we're going to learn what this stuff are, in order to get the bit pointing in the direction that he wants it to. Okay, but before we get there, let's talk about applications and configurations of directional or horizontal wells. Directional drilling is used in a number of operational scenarios, the most recurrent of which are sidetracking. We had this problem when we got stuck. We had to cut off, cement what we left behind, and then go around it. That's sidetracking. Inaccessible locations, for whatever reasons. Salt dome drilling. Sometimes you don't want to drill through salt, or sometimes you don't have any option. Salt mixes with mud, increases its salinity. Weird things are happening after that. You want to avoid that. If you can, you want to avoid faults. Faults bring some crazy wellbore stability issues. Okay, there are some faults that you drill through them as if they are not there. There are some big faults, and that's when the directional driller is very aware where the big faults are when you are drilling. He requests that from the geologist, from the operator company. The operating company, they have a geologist. The geologist did a survey, a geologic survey, or looked at geologic surveys before deciding where to drill, and he's gonna award the directional driller if there are faults known in that area that are of high resolution. He's gonna let him know so that he's aware, and the directional driller would either try to avoid them, or if he cannot avoid them, he would be very careful when they are through. Because it's very, very, it can be very, very, you can lose your hole like that. I mean, yeah. I had one time a directional driller we had a little bit of an issue. It was 2 rigs. One rig was vaccinated people, and the other rig was unvaccinated people. It was during COVID time. And there were, it was the same operator, different contractors, and the way it was like the directional driller, it was the same company, man. It was severely overworked person. It wasn't even the company's company, man. It was a contractor by the company. And poor guy, he had to move from one rig to another like crazy. He had a little buggy to go from one rig to another. And what happened was the directional driller was screaming to the geologist on the other rig that he's about to get, he's expecting to get to go through a fault in this stand as they were drilling, like middle of this stand, we are gonna go through a fault. And the geologist was like, what are you telling me that? I mean, I'm not gonna know anything until 1 hour after when we start getting cuttings from that depth. You know, if you think you are somewhere, you are probably in it already by the time I know that you are in it. It was like he got very excited, that directional driller, and forgot that there is this lag time. So the cuttings coming on the surface, they are not from the depth that your bit is in right now. It takes about an hour for the cuttings during normal drilling operations to make it to the surface. So we need to take account of that. Okay, it's taking time for these cuttings to come to the surface. So by the time the geologist figures out that we passed through a fault, you are already in it, you know, or you already passed through. Multiple exploration wells from a single wellbore. This is what we do these days. We drill from a pad. We drill a pad of wells. Those two wells I told you, one rig was drilling 4 wells, the other one was drilling 3 wells. And there was a time when one rig was on oil-based mud, the other rig was on water-based mud. And the people working with oil-based mud get more money because they give them extra pay every day because they're gonna need new clothes eventually. But yeah, you cannot avoid oil-based mud these days. Like just like you cannot avoid shale. It's like in your career, I guarantee you that you're gonna be dealing with shale. Also, if you go to the field, I guarantee you, you're gonna deal with oil-based mud. Eventually, you become allergic to it. One time, I found oil-based mud between my toes. Can you imagine? Anyway, well, one time I had to get into I was helping some people replace the screens of the shale shaker, and I literally got into the shale shaker, and I slipped. And that was ridiculous, but that's disgusting. Anyway, multiple exploration wells from a single wellbore, offshore multi-well drilling. Yeah, offshore, everything is expensive, okay? The lease for the rig offshore is over $1 million. It can be over $1 million a day to lease a rig offshore. Cost you $1 million a day. So every hour, every minute counts, you know? So the costs are like, I don't know, $1.5 million a day. So how fast you drill that well is important, or how cheaply you drill that well is very important. So you go as fast as you are safe, but you go as fast as you can. Relief well. That is important. That's when you have a blowout and you want to go from the side, intersect the well that has blown, and inject cement to plug it. Okay? This well won't be vertical. I guarantee you, it will be directional. And of course, horizontal wells, which is more production development kind of well. You know where the resource is, and you want to drill vertically, kick off a turn, land into the target formation, and then go horizontally across it and suck the oil through it. Fracture this horizontal well and suck the oil through it. This is a technology used in shale and is proposed to be used in geothermal, drilled through two horizontal wells, inject cold water from one, have it pass through the hot rock and make it to the other well, and then produce hot water from that other well, because as the cold water will go through the rock, it will heat up, become steam, or warm water, hot water, and come out from the other well, turn a turbine, or harvest this heat and create energy from it, and transfer energy from it. The thing with geothermal is that there is not a lot of, to excuse the hype that is happening. A lot of the stuff that you hear about geothermal is just plain enthusiasm. Okay, everybody's enthusiastic about geothermal because it has this thing that basically, how do you say it nicely, it brings the left with the right together. And for petroleum engineers, it brings the environmentalists and the petroleum engineers together, you know, apparently. But it's, I mean, the hype is too much for, you cannot have an economy based on geothermal. Now, in the future, there is a source of natural gas called hydrates in the ocean below the seabed in the ocean, oceanic natural gas hydrates. Those are at the fairly like 1,000 feet below the seafloor, and they are ice with natural gas trapped into it. And the volume, the amount that is available is huge, huge. But it won't be cheap as shale is now. I mean, if the price of oil goes high, of course, hydrates are going to become very, very, they're going to become economically attractive. They were very economically attractive when I was a senior in Texas, because the price of oil was very high, okay? So any energy source was investigated, and there were a lot of grants given for hydrates. But the difference between geothermal and hydrates is that for geothermal, the amount of resource makes sense, okay? It's just not the time. It's gonna be, probably it's gonna be next century or something. But the way that these geothermal, hydrate resources are going to be exploited, it's very similar to the way geothermal resources are proposed to be exploited. You drill one horizontal well and another horizontal well, and you basically, from one, you inject chemicals and you destabilize the ice so that the natural gas is released and produced from the other well. And sometimes those wells are sharing the same vertical trunk to make it easier and cheaper. Anyway, I have to go because the other professor is outside waiting. Don't want her to get upset. I have a lot of people upset with me already. So anyway, thank you very much. I will see you all on Tuesday, and most likely I will post homework for tonight or tomorrow. And we'll go over it on Tuesday. So thank you very much, and I will see you all. Have a nice weekend, and I will see you all next week. Thank you. Thank you, Donald.
Thank you.